Uh, so let's start by have a quick review for what we learned in the at the end of the last class, okay? And so it's like a warm up, so that we can continue the topic. Firstly, okay, in the last class we're introducing a concept which called stress. Okay, so first thing, stress is not force, okay, and is the force per unit area. The second thing is that stress is only for the surface force, okay. We are not using the body force for the stress. And stress is can be further classified into two groups: normal stress and shear stress. So normal stress we usually using sigma and II. This I, if in this Cartesian coordinate 3D, this I can be either x or y or z. Okay, so I can be this can be sigma xx, sigma yy, or sigma zz. So it is determined by when this surface area go to 0, and the normal force on that area's normal direction, the differential over the surface area. Okay. And example of the normal stress in the fluid mechanics, usually we only need the pressure. Okay, it can prove that later on, pressure is kind of normal stress. So what does that mean? Pressure has the unit Pascal, right? And we know that Pascal is basically the force, the Newton per meter square. So pressure is a kind of stress, is a normal stress. The second type of stress is we know is that it's called the shear stress, in which way that the surface force, this F, may not in the normal direction of this surface area. Okay, and so it can be denoted as tau Ig, and the two indices. Okay, the first I is the normal direction of the surface area, so it's for AI, and the second J is the tangent direction, okay, of the force. So both I and G, okay, can be either X or Y or Z, okay, in 3D rectangular coordinates, okay. And so this picture on the right-hand side shows that if you have a cube in the fluid, right, so how you can calculate both the, so it will have 6 faces, right, and on each face you can have one, you can become one normal stress, and also you can decompose the any shear stress into two shear stress on the major XYZ axis. Okay, and for the shear stress, for this cube in the fluid, right? So we introducing the concept of control volume and the system in the chapter 1. Okay, so you can consider that this is just a control volume in the 3D rectangular coordinate. And if this control volume go to very small, okay, go to a limit that the volume of it is going to 0. So this control volume will collapse to a local point on the fluid, right? So in that case, in that situation, okay, the left surface and the right surface will collapse to 1. The front and the end surface will collapse to 1, and the top and the bottom will collapse to 1. So what does it mean? That means that on any points on the fluids, right, we only need 3 surface to define those stress. Okay, understand what I'm talking, right? If this the volume, this control volume go to 0, so all this control volume collapse to a point, and so you only need the calculate the this front and bottom, left and right, and top and bottom, front and behind, they will collapse. So you only have the 3 surface left for a single point. Okay, and this surface, this 3 plane can be X plane, Y plane, and Z plane on this across this point. And in this way, you can if you want to calculate the stress on this point, you only need this 9 elements. Okay, so on X, the first row is that those are the stress on this X plane across this point. And this sigma x will be normal stress, and you will have tau xy and tau yz as their shear stress. And the second row will be the stresses on the y plane across that local point, and the last one will be the stresses on the z plane across those local points. So in the other way, okay, we can group this all these 9 elements in a stress tensor way, and we're seeing that okay, this tensor, this 9 element, we group in this way mathematically. It can it represents all the stress information, the stress data, applied on this local point. Okay, so that's the usage of it. And there is a direction notation for this stress tensors, stress terms. Okay, so basically means that if you're looking either sigma I or tau ij, okay, you have both I and you both have a area, surface area's normal direction, and also has a false direction. Okay, so if this surface area normal direction is in the positive x or positive y or positive z, so we know that this is in the positive direction. And also for the false direction, if this false direction is also in the either positive x or positive y or positive z. Okay, so in that cases, both the area and the false, there are in the both positive directions, or if they are both in the negative directions, so we consider that this stress is positive. Okay, if one of them is positive, another is negative, they are not in the same direction, but not direction. Yeah, not either. They are not both positive and both negative. We consider it's the stress negative value. So let me give you an example. Okay, I'm using the pressure as an example for you. Okay, so consider that if we have 2D cases. Okay, so this is a fluid element. Okay, so this is x, and this is y. Okay, so for the fluid, they will receive a pressure force from the top, for the left, from the right, right? So this is the pressure force coming from all places. So this pressure force is a normal stress. So we are using the tau delta, okay? And let's look at the one from the top, okay? So for this one, the P is in the, so for this one, okay, the force, okay, force is in negative y direction, right? So it's because it's going down. And also the normal direction of this top surface for the area, okay, their direction, this A of n, this A, their normal direction is in the positive y direction, right? Because area normal direction. So in this case, they are not either both positive or negative. So in this case, when we not write this sigma y and y, right? So this is a sigma yy because that the surface area is on positive y and the forward direction is on the y. So this will be equal to negative p. Okay, if p is a positive value, okay. So by this notation, we're seeing that this will be negative tensor. So you can do the similar things on this on the left hand side, on the left hand side, right side, bottom. You will also similar get that this is sigma x will be minus p. Okay, so this is an example for the normal force. But what about for the shear force? So for the shear force, like one example we can have before is that if you have a plate in the bottom is stationary, and on the bottom there is a plate going high velocity on the right. Okay, so due to the friction between the top plate and the fluid, right? We will have a this direction on the top to try to drag the fluid on going right. So that's looking like this force here on the top one. Okay, in this case is so what's the force? For the force is in the positive x direction. Okay, and for the normal direction of this surface area, so the area is in the positive y direction. Okay, so both are the positive sign here. So in this case, I can write this tau yx equal to just equal to this tau y positive is just I can write this positive is a positive value. Okay, by this way.
Professor.
Yes.
For this shearing force, the way that I guess the fluid deforms how the bottom stays fixed. That's the no slip condition.
Yeah. So it either will share, either will deform in like this way. Yeah.
Right. No, I just wanted to understand what the no slip condition was.
No slip condition means that basically means that at the interface of fluid and solid, they have the same velocity. That means no slip. So that on the bottom will be stationary, the fluid will be stationary because bottom plate is stationary. On the top, the fluid will also have the same velocity as the fluid. So that's why it's become to stream, because there is a velocity difference on the top and bottom for the fluid.
All right, thank you.
No problem. Yeah, so in this cases, I can write this tau y(x) is a positive value. So why we define this it has this direction notation is like if we the way we make it the way we define like in this way, we will if you look at the deformation of this liquid, we make that all this deformation which you try to make this liquid deform in this kind of clockwise direction. Okay, for this shear stress, we make it positive. And if you try to have a force try to deform this liquid, okay, in a counterclockwise direction for the shear, they will be a negative value. That's the meaning that how we for the shear stress, how we define whether or not if it is positive or negative. So for example, if this tau is on this direction, then this force is become negative value, but the area is still normative value. So this tau will become negative value. And the effect is that they try to, deform this fluid in this direction, right? In this counterclockwise direction. Okay, so this notation basically means two things. Okay, for the normal direction, okay, it has this kind of definition. For the shear stress, okay, it basically means that we consider that the shear try to make the fluid deform in a clockwise direction to be the positive. Okay, and another thing that we are talking about in the last class at the end is that to calculate the viscous effect, right? So this is something we discussed in the first class, okay, the chapter 1, is that we try to distinguish the difference between the solid and the fluid, right? In the solid, basically, we are seeing that if it's an elastic solid, the stress will be linear dependent to the strain. Okay, so strain, we can consider strain is that the change of this angle gamma here. Okay, and sorry, not the change, is this angle gamma here, this value gamma angle here. And so in the solid, we know that we are seeing that stress tau will be equal to G, a constant times gamma, if it's elastic solid, and this gamma is the angle in radian, and this G is called the shear modulus. Okay, and in the fluid, okay, and I add a term called the Newtonian. I will explain this later, but you can just think that the Newtonian fluid is just like a common fluids. Okay, that general fluid we usually we see daily, like water, like air. Okay, for the Newtonian fluid, okay, the stress is linearly directed, not strain, but strain rate. What's the difference? So this is a strain, it's gamma, its unit is radian, and strain rate this angle is theta, right? Strain rate is theta dot. Okay, theta dot is equal to d theta dt. Okay, so the union is radian per second, and for this one, gamma is just radian. So now you see the difference between the solid and liquid, right? Liquid is like this stress is proportional to theta dot, okay, per radian per second, and for solid is tau is to the radian directly proportional. Okay, so that's why it's deformation in big. You can also think that because that why is it theta dot? Because that for the liquid they can deform continuously, right? It's like so let's see that the rate of the change that is more important. But for the solid, at some point, they can only deform to an angle, and they won't able to deform, constantly. So that's why it's only related to the angle itself. And this coefficient, okay, of this linear dependency, okay, we call it mu, and we call it viscosity. Okay, so this is where we stop in the last class. We introducing the mu. Okay, And also, oh, not there. And there additionally, okay, in the last class we try to calculate a strain rate in a very simple 2D cases. Okay, this is 2D problem. You have X here and Y here, a fluid between two plates, and the top plate is moving with suddenly moving velocity. And in the last class we prove that, okay, here I'm using alpha. Okay, this is still the angle. Okay, we prove that this is strain rate. This d alpha change of the angle over dt will be equal to the just equal to this du dy. We approved that in the last class with this correlation here. If you forget it, you can try to go back to that note. So it means it's telling us that you know, in these 2D cases, rectangular cases, the deformation, okay, if you only have this, if you only have this tau, okay, what's the stress direction? It will be this one, right? Because that for this fluid, they require shear stress in this direction, because that the top plate will try to drag this fluid go to this direction. So this will be direction on this here, and so this tau will be what? How do we write the notation? It will be tau. The first indices should be the normal direction of the errors, right? So this is positive y, so it's y. And also the second note indices will be the direction of the force. So it's in the x direction. So it will be tau yx. And also is that both, because both the area direction and the force direction in this case is positive, right? So this will be notated as a positive value. Okay. So this tau yx basically will be proportional to deformation rate, as we mentioned earlier, right? Will be proportional to this deformation rate. And since the deformation rate can be also write as this du dy, which is the u velocity gradient on the y direction. Okay, so so at the end we can write this tau yx will be proportional to du dy. Okay, tau yx to proportional to du dy, and this y is for the this surface area, surface normal direction, and the second x is for the velocity direction. When you know basically for this x positive x direction. And then for the Newtonian fluid, we know that their proportionality is constant. So we add that mu viscosity there. So the final one we can get is tau yx equal to mu du dy. Okay, so this is where we stop at the end of the last lecture. We're showing that for this 2D, okay, this is only for 2D, okay, for 2D flow, okay, and if you have a u velocity gradient, okay, and also then the tau yx itself means that the shear stress on the normal y direction surface and on the positive x direction, okay, if it's positive value, okay, it will be equal to mu du dy. Okay, so this force here, try to drag the fluid on this one. This is tau yx. Okay, and so this is the so-called Newtonian fluid over here. Okay, and this mu here is called the absolute viscosity or dynamic viscosity. Okay, either one is fine. The reason that we add this absolute and the dynamic term here, word here, is because there is another viscosity definition. Okay, so right now, so this is mu itself will be called the absolute or dynamic viscosity. And so let's go back to the physics, right? So what is really a viscosity it is, right? So why this fluid has viscosity? Right. So this is some behavior, right? So we have the fluid flowing through different tubes, right? And if the fluid with lower viscosity, like the water, okay, they will just flow very quickly, okay? And if this fluid with a relative higher viscosity, like the oil, so they may be fluid like a, you know, lower velocity. And if this fluid viscosity is even high, like the honey, okay, very viscous, then maybe the drop is like this way. And again, okay, if the fluid become more viscous, like your candle is melt, okay, those melted liquid, they may even cannot, you know, flow out if this tube is small enough. You know? So this is showing that what the with, you know, some feeling like what the with different if the fluid has different viscosity, it will affect their motion, right? And so viscosity itself, okay, you can consider that you know, the it's considered as some kind of internal friction of the liquid. Okay, it's like if you're looking at this picture here, okay, and you know, when the top plate is moving, right, you can try to you know artificially, okay, thinking that this fluid in some cascade way, okay, they have different layers here, okay, and the top layer will try to move with the same velocity with the top surfaces, and the top layer will try to drag also, you know, because this is internal friction, they also try to drag the, you know, so this layer also has the going right, has the velocity. So this friction, internal friction force here is also the same tau value on the top, and not same tau, okay, is some internal friction there. And so this kind of, if you're thinking, when it's a two adjacent layer of fluid, okay, they are if it's in the relative motion, which means that they are have some relative velocity, okay, have not, their velocity not same, okay, they have some relative motion, then there's some kind of friction will be generated inside of the fluid, and this is so-called viscosity, okay. So these, in the other word, okay, viscosity itself is a fluid properties, okay. As I show you here, so different kind of fluid will have different types, different values of viscosity. Okay, some fluid has lower viscosity, some fluid will have higher viscosity. And what's the unit for the viscosity? This mu here. So let me write. So this is mu. Okay. So mu viscosity in the SI unit is kilogram per meter per second. Okay, and so in the British unit it will be slug per feet per second. Okay, and if in the EE it can be right the pound force second per feet square. Okay. There is another very commonly used viscosity unit, which is called the poise. Okay, so basically one poise is defined as 1 gram or 1 centimeter per second. So you can quickly write the correlations, right? So if I try to write this as meter per second, what the value will be? Anyone? What the value will be? What's the coefficient here should be? Can anyone tell me? No? So this is 0.1, right? So you just write this 1 g of centimeter per second. You can just write this 1 of 10 to minus 3 kg, right? So because 1 g to time divided by 10 to minus 2 meter, right? Because this is centimeter times the second. So you do this, you get this is 0.1, right? Kg per meter per second, right? And so this is another popular unit we use for the viscosity. And sometimes we also writing this poise as CP, okay? CP is centipoise, okay? Is centipoise, just like a centimeter to your meter, okay? So 1 CP, you got a 0.01 T poise, okay? So this is just some units commonly used for the viscosity. I told you that we call this mu called the dynamic viscosity or absolute viscosity, right? There is another definition of viscosity, it's called the kinetic viscosity. So the relationship between the kinetic viscosity nu and dynamic viscosity mu is that only biodensity. Okay, so the kinetic viscosity nu is equal to mu divided by rho. Okay, so correspondingly, okay, so the unit for the kinetic viscosity will be this one, meter square per second, feet square per second, and feet square per second for E system. Okay, so this is just some introduction for the viscosity. And any question here so far? Anyone?
In what situations would we see dynamic viscosity, and in what situations would we see kinetic viscosity?
The situation you need dynamic viscosity is this situation if we want to using this Newton's Newton's viscosity law. Okay, if you want to calculate tau yx, then this one has to be using the mu. Okay, in the other one, if you want to using the kinetic method, then you have to times another rho here, times du dy. Okay, so this can be with kinetic velocity. So just make sure that if you want to calculate tau stress force from this velocity gradient, this one has to be mu, or or if you have nu, you have to times another density.
Okay.
Yeah. Any other question? No. Okay, so let's go to an example problem. So this problem will help you to get familiar how to calculate those stress shear stress, okay, viscous stress, based on this velocity gradient and the value of the viscosity. Okay. Please read this problem description. All right, so let's go through this together. It's same thing, okay? There are fluid between two plates, and the top plate will suddenly moving with a constant velocity. U will be 0.3 meter per second, and we know that the velocity distribution is linear distribution. Okay, linear velocity distribution. That means that at the bottom will be 0, at the top will be u equal to 0.3 meter per second, and then in the middle of the fluid, the velocity will be straight line. Distribution will be straight line. And we also know the gap between the two plates, d equal to 0.3 millimeter. Okay, with this gap, and because it's a linear distribution, we can directly calculate du dy, right? So in this case, we can directly know that du dy will be just equal to this u divided by d, okay? Because it's a linear distribution. The first question is basically some, I think it's unit conversion stuff, okay? We know that mu is in this one centipose. Okay, the unit is centipose. Remember what I mentioned, given that what's the meaning of centipose? Centipose is equal to 0.01 poise, and 1 poise is defined by this by this unit. Okay, and we want to convert this one centipoise to pound f second over phi square. Okay, so this is how we do that. First, we have this 0.65 centipoise, right? First, we convert the centipoise to poise with this 0.01 correlation, 0.01 correlation. So by here, we convert it to the poise. And this is the definition of the poise, right? The definition of the poise. So by times this term, we convert the poise to this definition, to this term, to this correlation. And the last one is that we want to change this one to the this one, pound f, right, as feet square. The first thing is that the first thing I do is that I change the gram to the pound mass by this correlation, and then similarly I also change the change the pound m to the slug. So all these terms help us to change this gram to the slug. Okay, and then we time this term to change this centimeter to the feet, and at the end, okay, we've changed this this slug, okay. We change this slug mass term to this LB force. So this basically will give us this is equal to some LBM times gravity, something like that. So this will try to convert the slug to this kind of mass term in this E coordinates, okay, sorry, E units. So this will be the final result. So this is pure unit conversion things, okay. And so what the second question is calculated the this kind of kinematic viscosity, or nu, okay. Kinematic viscosity is nu, so that it has to using the mu divided by rho, right? And the given we do not know the rho directly, but the equation, the problem telling us that we know the specific gravity, right? So knowing that the definition of a specific gravity is equal to rho divided by rho of H2O, right? So this H2O is some standard density for the water. And so this is pound AA. And so mu divided by rho, mu divided by this Sg times this rho of water, will convert it to the rho, okay? And this is the mu value we calculated on the first term, on the first question. And further, we do some. This is that Sg value, and this is the water density here. It's 1.94 if in this British unit. Okay, and so after you get this density, and we try to convert to cancel those faults, because this is the unit system for the EE. This is the unit system for the British. Okay, so we change this slug with this mass in the mass in the EE system, and again we also change that later on at the end we also change the feeds to meter, feed to meter, because that result we want to meter. Okay, by this way we cancel everything, and we got the new kinetic viscosity. Okay, it's also just a unit conversion. Okay? And then the first two questions is pretty simple. It's for the unit conversion. And starting the next problems, the question C is really asking us to calculate the viscous force, right? So viscous force tau equal to mu times du dy. And du dy is just equal to u divided by d, right? It's this u divided by this d. And so it will be some, there will also be some unit conversion things, because this u divided d here, this is in some kind of SS units, right? And mu we derived before, in this one is in the EE unit system. So we just need to convert this, this velocity gradient to the EE system, then we'll be able to get the tau. And this tau will be the tau yx, okay? And then because on this direction, so it will be positive value. So this is du dy will be equal to u times d, and this is with the value, and it will be separate. So we get this value here, and times this mu here we calculate from the question A. We can directly get the result. Okay. So this will telling us that how to using this Newton's, if it's Newtonian fluid, right? If how to calculate this shear stress, right? So remember, this tau is not a force, okay? This is shear stress, is Newton per unit area. And if you want to calculate the force on the top, you have to using that tau times the area, the surface area of this plate. Then you can convert it to the force. Okay. Similarly, since we want to calculate the lower plate, the tau on the lower plate. So on the lower plate, we will have the same velocity gradient. Du dy will be same because it's straight line. So we have same gradient and the same mu. Okay, because of this mu is constant across the fluid. And in this case, is so what the shear force will be at this surface? It will go into this direction, right? Because at this bottom plate will try to drag the fluid on this direction to make this fluid and the bottom part to stay stationary, right? So this will be tau. What's the first one? First one is y, right? It's still y in the y direction. Even so, it's the negative y direction, and also in the negative x direction. Negative y, negative x. So both are negative. So this is still a positive value. Okay. So it still be mu du dy. It's still positive value because that this is negative direction, both negative direction, then they are positive. So result are positive. This is the notation we use to determine the sign of this shear stress. Okay, and also in a straight way you can, another way you can feeling that this tau at the bottom, okay, is try to, if you think that this is like some kind of rotation, this is like try to rotate this fluid in this clockwise. Okay, that's why it's also larger than 0. And so basically we will get the same result. Okay, problem D and problem C should give you the same result. The only difference is that in problem D, the unit they want Pascal instead of this EE system units. So you just need to do additional, unit conversion, just to convert this one to the to change it to the Pascal. Pascal is a meter, so in Newton per meter square. Okay, so this is Pascal. Pascal is just Newton per meter square. Okay, so Pascal is also a unit for the stress. Okay, I mentioned it before, and so this will be the result. And the last question is that to the direction of each shear stress calculated in part C and D. Okay, so this question is not very clear, to be honest, because they are asking that the direction with shear stress. Okay, they are not talking about this shear stress is on the fluid or on the shear stress on the surface on this place, right? If it's on the fluid, we know that on the top the shear stress is this way, on the bottom the shear stress is on this way. But if you are looking, this is the stress working on the fluid. But if you are thinking about that, what's the stress working on the plate, then that is another story. If I want to see that what's the stress working on the top plate, we know that it will be this one because the fluid will try to, give to friction, try to hold on this plate from the moving, right? And on the bottom is same thing, right? On the plate will basically have a stress on going to right because that this viscous force, right? Due to the fluid motion, this fluid motion will also try to bring this plate going to right, but the plate will fix there anyway. So in this solution, okay, the textbook basically is define the stress is on the plate, not on the liquid. Okay, so it's from the upper plate, so that means that they are considered the stress on the plate. So that's why on the top is going to left, on the bottom is on the right. So this stress is on the plate. Okay, so on the plate surface. But if you are talking about the stress on the fluid, then it will be inverse of this two. Okay, and any question? So when we finish this example problem.
I have a question about the notation.
Okay.
So I understand that the shear stress is obviously like parallel, like on the plates and stuff like that. But before, when you were giving the examples of in like 3D space, how do you know if there was one that was perpendicular to a plate? So like I see that all the tau stresses are on the plane, and then the sigma stress is perpendicular, obviously. But
yeah.
like, is it is it like using the right hand rule or something?
No, it's not right hand rule. No, we do not think that. The right hand rule is from this coordinate system definition, right? The x, y, z, the way we define it. And it's not, okay. So the reason we draw this one, and you see that it's going to right, is we just assume that it is a positive value, okay. And it's in the positive value. You can also draw it on the left, okay, in this case. So, but that will become negative value because the reason we draw this to the right because that this is the positive value for this value, okay. Because that we define the positive value that when both this normal direction and the force is in the positive, this is the positive x direction, okay, and also normal. This is positive y direction. So that's the reason when I draw this way, this is the positive value for the top. Okay, so if I draw this direction, then it becomes negative value for this one.
Okay, so I just don't get why, like, when tau would be positive or negative, then would it just be the direction of the force and like our coordinate system? So in that example that you're using, tau y of x is positive because it's going along the positive axis, and yeah, it's just going on the positive x-axis.
You cannot do that, okay, because that is tau is defined by two things, right? One is force, one is error. So error is also has a direction. Okay, so it's like this tau contains the direction info of two things. Okay, that's the reason that you cannot just using a single x or y z direction to define it. No, you have to you have consider both direction of the force and both direction of the error. You know what I'm talking? So that even this force is positive, okay, but if this error is negative, then this is negative. Okay, if this force is positive, error is positive, then it's positive. If this force is negative, error is negative, they are both negative, then they are still
positive.
Yeah. So you cannot just using one direction to determine this one. You have to consider both contribution direction factor on the force and direction factor on the area. So that's why I'm saying that when you have this shear stress, basically, you know, if in the shear stress, right? So this will be on the top, right? This will be top. This is the positive direction. This will be positive direction. So the effect is like you try to, you know, deform this liquid in this clockwise. So this we consider this clockwise as the positive direction, and on the other hand, this will be like a negative tau, and this like will be negative tau. So in this way, it's like you try to, you know, deform this fluid in this counterclockwise direction. So this will make it positive tau. So it's just the notation like we want to this tau. The physical purpose of this shear stress is try to bring the deformation, right? So it's like a this you do the deformation in this way in the clockwise, you will be positive, and if you do the deformation in the counterclockwise, it will be it will be negative. That's the whole meaning, okay, of the shear stress.
All right, thank you.
Yeah. Any other question? No question? Okay, so let's continue. We're using the word Newtonian fluid, right? So basically means that this correlation tau, which is equal to a constant times this velocity gradient, you know, is only working for Newtonian fluid. And what is Newtonian fluid? And I told you that most of the common fluids we have in our daily life, they are Newtonian fluid. Is water, is air, is you know, other kind of, you know, common liquids you have or common gas you have, they are all Newtonian. But there are also some kind of fluids is not Newtonian, okay? And then those kind of fluids are called non-Newtonian fluid. For non-Newtonian fluid, okay, they will not satisfy this. So this in this case, for the non-Newtonian, you won't able to write this, you know, du dy, okay, yx. You won't able to write this. It's not equal. You cannot write this kind of thing. And so I write a star here. Okay, basically means that this part is optional. Okay, this type of content is optional, is not required by the exam. So I will basically just give you, you know, some basic introduction. And if you want to read it more, you can go to a textbook. For non-Newtonian fluid, basically any fluid, okay, if you cannot calculate the tau in this way, then we call it non-Newtonian fluid. And usually the most you know, commonly seen non-Newtonian fluid is these two types. One is called the power law fluid, and one is called the Bringham plastic. Okay, so for the power law fluid, basically you won't be able to write tau x to mu du dy. Basically, and in the other side, it has to be k, a constant. You can think in this case something similar to viscosity, but to du dy to a power of n, and n is a constant. Okay, and furthermore, you can even, you know, try to rewrite it a little bit in this way, you know, to write this n with two terms. One is n minus 1 term, and one is itself. And this times this one will go back to this n. And if you write this notation in this way, you can think that this is something similar to what we have mu before. And we call this eta, and this is called apparent viscosity. Okay. And for the based on the this power law, this power law exponent coefficient n, okay, value. If this n is smaller than 1, we call this pseudoplastic fluid. An example like your pens, okay, modern pens, like your, you know, whipped cream, okay, you know, the reverse sticky, those kinds of things. They are not Newtonian fluid, okay. They are this kind of so-called pseudo plastic fluid. And so you have to, if you want to calculate the viscosity, you have to use this kind of correlation. Okay, find the k value, find the n value, and you're able to calculate the tau. If this n is larger than 1, this is called dilatant fluids. One example is that if you have corn starch in the water mixed with the water, there's some example here. This is one kind of non-Newtonian fluid. Okay, another kind of non-Newtonian fluid is called the Bringham plastic, and in this one, okay, it's like a you know, the viscosity has to be calculated in this way. Okay, a term proportional to the velocity gradient, and also a constant term. Okay, and So example of this kind of fluid, you can think your toothpaste, you know, it belong to this Bingham plastic basically. So this is just some fundamental introduction that it's not all the fluids we can consider is a Newtonian fluid. Okay, Newtonian fluid is the most common fluid we've seen, and if it's Newtonian fluid, we can directly using viscosity times the velocity gradient to calculate the shear stress. But if it's non-Newtonian fluid, either they are power law fluid, Bingham plastic, or some other kind. So you have to using their own special, you know, correlations to calculate the viscous force. Okay, so it's just some fundamental introduction here. I won't go too much details here. And this is some picture for different kind of thing. Okay, fluid. And so here we finish the topic of the viscous effect and the viscosity, you know, Newtonian fluid for the Newtonian fluid. And the next topic of this chapter is the surface tension. Okay, so what is surface tension? You know, and what's the physics behind it, right? The surface tension we can see it in our daily life, right? So if, for example, this is a water strider, they can, you know, walk on the surface of water, you know, and without sinking inside, right? So because this you have you have surface tension between its feet and the water surface, right? And when you have blow a bubble, and this bubble, we know that it's a thin film of liquid, right? This bubble is thin film. And inside this bubble will be gas, outside of this bubble is gas. And why this bubble is in this sphere shape, right? Why is not other shape, right? Why it cannot be the square, can be triangle? And also that if you have this dew on a leaf, right? And why this dew can be, you know, if it can be this you know, drop like something like this is sphere shape. And if you have water, you know, small, very small water coming out from a faucet, at the edge of this faucet, you see that this droplet like of water will stick to the faucet without dropping down, to against gravity at some extent, right? So why this can happen, right? And this is because of surface tension between the edge of the edge of the surface. And so what is really the physics behind the surface tension, right? Why as the interface of the you know, gas liquid or solid liquid? Why we have as an interface we have this surface tension? One thing you need to know that surface tension is only for liquid. Okay, not for gas, not for solid. Okay, so one keyword is this keyword liquid. Anytime when we're talking about the surface tension, is only for the liquid, and it's only between the surface. So if this is liquid, and this is gas, so we may have the surface tension at this interface. And a similar thing, okay, if this is liquid, and if this is solid, we can also have the surface tension on the interface. Okay, so the first keyword is that the surface tension is for liquid. Usually for the, actually theoretically, you also will have the liquid surface tension for the gas, but it's just too small, okay? It's very small for the gas, so usually we just neglect it. So that's why is that commonly speaking, when we're talking about surface tension, we're focusing on the liquid. And the second thing is that why we have this, where this force is coming from, right? Why this force is coming from? So take a look at this picture. Okay, think about this is liquid, and this blue particle are the molecules of this liquid. Okay, and between the particles, the blue between these molecules, okay, these blue dots, they will these molecules they have the attraction force between each other. Okay, so if you're looking a molecule inside of the liquid, okay, this is an example of a molecule inside the liquid, right? So this molecule will receive either the attraction or repulsion force from the surrounding molecules from all directions, right? It will return the either attraction or repulsion on this direction, either attraction repulsion direction. So everywhere 360 degree. And the result of this is that if you sum this force altogether, it will, if this liquid is in the equilibrium state, okay. If you sum all this force from all the directions, it will become, at the end, it will become the zero. Not zero, actually. It will become as becomes the pressure of itself. Okay. So, if there has a gravity, you will have the pressure. If no gravity working on this liquid, it will become the zero. Okay. So this is when the molecules is inside of a liquid. But if you look in the molecules, okay, at the surface of this liquid, so what do you get? Okay, here we get the maybe the attraction force here. You will get the attraction force here. We will get the attraction force here. You will get the attraction force here. You will get the attraction force here from its surrounding molecules. But this is only something like 180 degree, right? So the top part has no force. So what the net result will be? So if all this we are the attraction force, basically they will try to drag this this surface particle, try to drag it to go to the inside of the fluid, right? Try to have something like the net force will be something like try to drag this particle to inside of this fluid. And this force, because it's not zero, the net force is not zero, and this force brings the surface tension. Okay, so that's why we have the surface tension, because that you know, the inner particles want to drag the surface particle go inside. Okay, and so in the other one, you can think that this surface tension is something like the force acting perpendicularly inward on the surface layer of the liquid. Okay, and you know, to pull its surface molecules towards the interior of the fluid. Okay, and so what's the result of this? So usually the result of this one is that you know, because we want to try to drag all these surface molecules to inside, right? So it will lead the result is that try to lead the liquid try to minimize its surface area. And that is why that when we talk about the surface tension, why this you know, bubble is sphere, is not rectangular or triangle, because that sphere is the shape that has a minimum surface area with a given volume. Okay, and similar thing for this dual liquid dual drop, you know, is similar like a sphere, right? That is also the reason. Okay, and furthermore, okay, so the surface tension is usually can be considered as a liquid properties. It's like a different you know, liquid, they will have the different surface tension. Some liquid they will have higher surface tension. Some liquid maybe has lower surface tension. Okay, so this is why we have the surface tension in a liquid. Any question here? Anyone? No? Okay. So let me continue. And we also need to, we talk about, right, the surface tension is between either the interface between gas and liquid or solid liquid. Let's focusing on this one. If you have the surface tension between a liquid and a solid interface. Okay, so this is a water droplet, not water, a liquid droplet, and it's on the surface here. Okay, and it depends on different liquid will be. You basically will observe two kind of behavior. One kind of behavior is this dew-like things, like those dew on that leaf, right? So the liquid will, you know, try to maintain in a spherical shape. And another one type is that, you know, the liquid will just try to, cover the larger area of the solid and become a thin film. Okay, the first cases we will call this non-whiting, because that the liquid is not likely to, to white to make this solid white. And the second case we call it whiting, because that this liquid will try to, white the surface, solid surface. And if you're using mathematically, if you're looking at the difference between these two is that you can define an angle of this surface, the liquid surface at the wall, and at the wall, this surface tangent direction with this wall direction. So this theta angle. So if theta angle is larger than 90 degrees, we consider it non-whiting. And if this surface tension direction of the liquid at this location, and with this wall direction, this theta is smaller than 90 degrees, we consider it's a Whiting case. And why we have this behavior? Right? Why this is some liquid like this, some liquid like this? It go back to the theory of this, the similar things we obtain here. Okay, the force between the molecules. So if this is if it is solid, okay. So at this interface, and this is solid, and this is liquid. And if you're looking at this interface, okay, so you will have this particle, which is so this particle is the liquid particle, okay, liquid molecule. You can see liquid molecule. And on the other hand, in the other side, they will have this is solid molecule. And on the top of this, we will also have other liquid molecule. On the bottom, we will other solid molecule. Okay, and between the liquid molecules, okay, they will have their attraction force. Okay, so this is called a cohesion. So cohesion is the attractive force between the liquid molecules. Okay, so the force here, this is cohesion. The cohesion to drag them each other, to attract each other. And also similar thing, okay, between the solid particles, because they are also the cohesion, because they are the same particle. So cohesion is not only for the fluid, okay. Basically, cohesion means that the attract force between the molecules of the same type. Okay, because this is the same type of molecule, this one, so they are all cohesion. And also we have another type of force, is called the adhesion. What means adhesion is the attract force between the liquid surface molecule and solid surface. Is that between this solid one and this liquid, they also have some force between this each other, this black one, this white one, and we call this adhesion. Why is adhesion? Because that they are not the same type of molecule. Okay, that's it. And for non-Whiting cases, it simply means that your cohesion force is larger than adhesion. The attraction force from between the liquid particles is larger than the attraction force between the fluid particle and solid particle. So that's why that they try to drag this force to back, so that it's forced to dual shape here. Okay, this is non-Whiting liquid. And for the Whiting liquid, on the other hand, between the liquid particle and the solid particle, they will have a larger attraction force than the attraction force inside the liquid. So that's why is that all those particles is more likely to go to stick with the surface rather than go back to the liquid. And in these cases, we call it the Whiting fluid in the Whiting cases. Okay, so now you see the difference, right? So non-Whiting is cohesion is the effect larger than adhesion, and Whiting is adhesion is larger than cohesion. Okay, is this clear? Does this make sense, guys? So this one is like the attraction between the liquids is larger than attraction between liquid and the solid. This one is the attraction between the liquid and solid is larger than the attraction between the liquid molecules. Okay, does this make sense? Okay, and so we have this after we have this non-Whiting and Whiting behavior. After we get this explained, so the next thing we can physical another fluid phenomena we can observe is so-called capillarity. Okay, so what's capillarity? Basically means that if we put a small diameter tube, a glass tube, okay, into a water, into a liquid, okay, water or mercury, okay, on some kind of liquid, you may observe that the level of the liquid inside the tube will be higher than the the level of the liquid outside the tube. And on the other hand, okay, for some liquid, you will observe that the level of the liquid inside the tube, this small glass tube, okay, with small diameter, will be lower than the the liquid depth level of the outside. So they will have two different effects here. Why? Because that this is due to the what? This is this. So if this will happen, okay, In this case, it will happen. This should be whiting or non-whiting fluid. Anyone tell me? Anyone? Just guess. This should be whiting or non-whiting. It should be this one or this one.
Would it be wetting?
Yeah, you are correct. You're correct. So this will be whiting fluid. Why? Because that, as I told you, that the whiting fluid is that you have a larger attraction force between the liquid and solid, right? So this is the case. You have a larger attraction force between the liquid and solid, so that you will try to, this force will try to, drag this liquid going up, and so that it can compensate some kind of gravity, right? Because it will drag this force going up, right? And then for this one is like this is non-whiting. It's because that cohesion is larger than adhesion, which means that the attraction force inside the molecules is larger than the attraction force between the liquid and solid. So it's like all this liquid will try to drag it, try to drag it inside of the particle, inside the liquid. So that makes it this is lower than the surface outside. So it's like and now you can also think about this from the angle, okay? And if you draw an angle, so this is non-whiting, so theta will be larger than 90 degree, and so if you draw this, so this is non-whiting, right? So this, if you draw this tangential direction, direction, and this line here, so this theta will be larger than 90 degrees. So theta is larger than 90. This is theta here. And on the other hand, for this one, if you draw the theta, so this will be tangent direction, and this will be theta. So in this case, theta is smaller than 90 degree. Why I already see? Theta is smaller than 90 degree. So this will become whiting. 90 degree whiting, yeah. So this will explain that why we see this capillarity effects. Okay, it's due to the surface tension, and due to the different type of fluids, right? It depends on whether they are whiting fluids or non-whiting fluids. If they are whiting fluids, it's likely make the liquid surface inside this tube become higher. If it's non-whiting fluid, it's mostly likely to make the surface level inside this tube become lower. Okay, and one example, water is a kind of whiting fluid, because we know that water can like to white you, right? White the body. And mercury, on the other side, is an example like a non-whiting fluid. Okay, we know that if you pour the mercury on a surface, and those mercury will more likely to form those small droplets, things like that. That's why it's because mercury is kind of non-whiting fluid. Okay. Any question here? So here I finished the topic of the surface tension. So for this part, basically in this class, we only need to understand the fundamental concepts behind the surface tension. Okay, we will not go to the very details of it. We do not need to like calculate if I give you the surface tension properties, what those force will be on the surface. No, we will not go that far. So this part is only try to give you some introduction with the basic concepts behind the surface tension. Any questions so far? Okay, no, that's good. And the last topic of this class, okay, oh, sorry, not this class, this chapter is chapter 2 is that some classification of the fluid mechanics. Okay, so we have many kind of fluid flows, right? So there are some fundamental classification there. We can classify the fluid motion by different ways. Okay, one way we can distinguish is by the geometry of the flow field. Okay, we can determine the fluid field to be either internal flow or external flow. Okay, what the internal flow means? Internal flow means that the fluid flow inside a bounded surface area. Okay, the flow for oh, I make this big mistake here. So this should be this typo here. So my fault. So this should be external. flow. And this one should be internal flow. So internal flow just means that the flow inside a pipe or inside flow inside a duct with some bounded area, right? So for example, if you have flow inside this, air conditioning duct, of the building, so this kind of internal flow. And if for the flow over airplane is going outside, right? So it's we call this kind of external flow. And sometimes in some cases that you will have both internal flow and external flow. Like this is the flow through a ramjet engine, okay? And before the flow go inside this engine, go into this air intake. So this is the external flow. Okay, the flow here is external flow going here, here. This is external flow. And after the flow go inside this combustor, because it's inside, so this become internal flow. And then there will be a nozzle here, try to give the propulsion force of this heated gas. And this is the internal flow. And but after this, your gas, reactive gas combustion results, okay, it's exhausted out. Then it will become external flow again. Okay, so external flow here, external flow here, external flow here, but internal flow inside. So sometimes it's a combined situation. So this is one way we can distinguish the one way you can classify the different type of fluid motion. And another way, okay, we use to classify the fluid motion is based on whether or not the density of the fluid is going to be changed or not. Okay, if the density of the fluid of this flowing inside this flowing motion is not changed, if the fluid density is not changed, we call this incompressible. And if the density can be changed, we call it compressible. Compressible means that you can compress it, right? When compress, the density is changed, right? That's why we call it compressible. Compressible means density can be changed. Incompressible means density cannot be changed. Okay, and usually, okay, when we're talking about this incompressible, compressible things, we are focusing on the gas, because we know that for the liquid, usually you won't be able to change the density too much, right? You cannot compress the liquid too much, right? But for the gas, right, we can compress the gas a lot. And so that if I compress the gas and reduce the volume, so its pressure and density will increase from those thermodynamics class we took before, that piston cylinder configuration we mentioned before, right? So what I want to see is that this incompressible compressible flow, when you have this kind of this kind of terms, usually we're focusing on the gas, and when we especially for the air, and so that's why is that these two terms is usually related to the aerodynamics. Okay, with those airplane, aircraft, rocket, and those kind of thing. Okay, and there is one special parameter which is called the Mach number. Okay, Mach number is defined by the flow velocity over the sound speed. Okay, speed of sound. And I think if you take your, the follow up of this class is 393, right? So if you take 393, there is your chapter will focusing on the compressed flow, and you will know that this Mach number basically can give you some measurement on how the density, to expressing the level of density change across the flow. Okay, and so if you take a look at this picture here, and the Mach number, when Mach number is small, okay, if the Mach usually, okay, when Mach number is smaller than 0.3, we will consider that they are incompressible flow. Means that the density of the fluid will not be changed too much. Okay, it's almost neglectable. And when Mach number is larger than 0.3, Mach number become larger. Okay, and then we try thinking that the density of the flow is not a constant anymore. Okay, the density will be a function of Mach number. Okay, and in that case, all the region here, they are compressible flow. Okay, all this is compressible flow. Okay, and this is one usage of the Mach number to it's like if it's the Mach number smaller than 0.3, okay, it's incompressible. If the Mach number is larger than 0.3, we call it compressible. Mach number is also be used in another way to distinguish the fluid motion. It's like if it's Mach number smaller than 1, we consider it's a subsonic flow. If Mach number is larger than 1, we consider it supersonic flow. Okay, so we can also use the Mach number to define the flow in this way. Okay, but basically Mach number you should know that the Mach number can be used to distinguish if the flow is incompressible or compressible. Okay, incompressible flow is like this, flow on the river, right? Its velocity is relatively small, so the density will not going to change. This is incompressible. And compressible flow, like this air fighter, we saw this kind of effect in the picture. You saw, maybe you know before. This is so-called the sonic boom. Why you see this? This is that when your air fighter is accelerated across the Mach number equal to 1. At this moment, it will transfer from the subsonic to the supersonic flight. And at this critical point, you will see this so-called sonic boom. So it's a kind of a Mach disk. Okay. So this is due to the compression of the air, the sharp, okay, the quick, the abruptly density change inside this area of the air will cause this kind of thing. Okay. So yeah, another way. Okay. So this kind of term is usually used in the aerodynamics. Okay, especially for this compressed flow is usually related to with this high speed flow. Okay, large Mach number flow. Also based on the viscosity of the flow, we can also distinguish the fluid motion be either viscous or inviscid. Okay, and viscous flow basically means that when this viscous effect is strong, and inviscid flow means that those viscous effects can be neglectable. Okay, one example is that this air, so this air flow over this airplane wing. Okay, so in the region, okay, very close to the surface. Okay, we will form a small layer. Okay, this gray region. This region is very close to this airplane wing surface, and in this small region, we will have a very large velocity gradient. Okay, and then therefore because that Newtonians, we know that tau equal to mu du dy. Right? If this gradient is very large, then we know this tau will be large, or if the mu is known. So in this case, in this small region, they are viscous flow because that this viscosity is large. But outside this small layer, going outside, some region here, some region here, some region here, some region, and there may not so much of the velocity gradient. The velocity here may be very close to each other, not large velocity gradient. And if you calculate tau, it's very small. And in this region, you can consider that they are inviscid flow. And similarly, since that is that if you have flow over a flat plate, and in the region close to the, this is so-called the boundary layer. So, and we can go through this later in the later chapters. So basically, it's a small layer very close to the surface of this solid plate, and inside this region is very thin region. We will have very sharp of the velocity gradient, velocity change, because the velocity will suddenly, quickly reduce to 0 as well. So in this region, because this larger velocity gradient, we know the viscous effect is very strong. We call this boundary layer, and this layer is viscous flow. And outside this small layer, and the velocity won't change too much on this y direction. So the tau is relatively small. We consider this inviscid flow. So this is another type of to distinguish flow region. And the last step is to distinguish flow motion is based on the for either flow is laminar or turbulent. So what is laminar flow? Laminar flow basically means that this flow is this thing looks like a layer by layer, right? The similar things we mentioned before. The flow is flowing like this layer by layer stuff. One layer flow like this way. It's very organized, and so in that case, we are calling it by smooth layer of the fluid. So by that way, we call it the laminar flow. Okay, this is the example of laminar flow you observe in the laboratory. And turbulent flow basically means that if it's the thing become very chaotic. Okay, so it's just like you open the faucet, right? if you open the faucet very small, give a very small flow rate of the fluid, you'll see the water is in a very organized way to going down. But if you make the faucet open very large and the velocity become higher, you think that you will see that the water coming out from the faucet will become chaotic, very chaotic way. And this chaotic is mathematically sometimes it contains some random behavior, right? It comes random behavior of it. In these cases, we call this turbulent flow. One thing you need to be realized that both laminar flow and turbulent flow belongs to viscous flow. Okay. When we're talking about the laminar flow, they are all for viscous flow, Okay. You just because that either this laminar behavior or this turbulent behavior is due to viscosity is related to the viscosity. Okay. So laminar flow and turbulent flow is belongs to the viscous flow. And there is also so-called transitional flow is like the critical point that where you transition from the laminar flow to viscous flow, to the turbulent flow, okay? And there is another parameter which we will introduce later on, like you can characterize that whether flow is laminar or turbulent. It's the so-called Reynolds number. And Reynolds number is defined by the density of the fluid times velocity of fluid times this fluid characteristic length. If it's pipe flow, it will be diameter. If the flow over the plate, it will be plate length. Okay, divided by the viscosity. So basically what this means is that if the flow velocity become larger, velocity become bigger, and your Reynolds number will become larger, it's more likely to get the turbulent flow. When Reynolds number is, and when Reynolds number is large, we would like to get the turbulent flow. And if your viscosity is relatively large, high viscosity, so the things are more likely to be organized, which means that when Reynolds number is small, you mostly like to have the laminar flow. Okay, so in the end, okay, so there are different ways to distinguish fluid motion. So this is a chapter. So this is a flow chart. You can thinking how we distinguish it. Okay, based on is viscous or inviscid, we can determine is viscous or inviscid, and also under the viscous, it can be laminar or turbulence. Okay. And in the meanwhile, okay, flow can be also determined by compressible or incompressible, and all the internal or external. Okay. Any question here, guys?
Nope.
Okay. So far so good. Here we finish this chapter 1. Sorry, chapter 2. And in next class, we will go to the chapter 2. So we will start chapter 3. We will study those fluid statics, okay, hydrostatic. And so for today's class, we have finished here. 3 things before I finish. First thing, okay, we will have an assignment on the value class, and you should be able to do it. Okay, it will be due next week, Friday. Okay, do not be late submitted. Okay, otherwise you won't able to get the full grades. And it will give you 3 trials, okay, for each problem. So you should be able to see the solution after you finish it. Okay. As I told you in the last class, your work, you need this. I will require you to show your work. Okay. So for the problem, it's better that you can, write your solution, the procedure, how you derive the solution in a paper, and then you either use your phone to take a photo, or you scan it to the PDF and upload it to the value class, so that later on, if you have any question, due to this automatic grading, I can investigate inside to see that if you can get the partial credits. Okay. First thing, the second thing, there will be a quiz for today's attendance. Okay. So there will be attendance quiz here. So please finish it before 3 o'clock. After that, it will be it will be hidden. Okay, so you won't be able to see it. So please finish today's attendance quiz on the blackboard. The last one, I made a survey on the same folder as the quiz that I want to take a look at whether or not you guys has the required equipment to are ready for the midterm exam, such as that if you have a PC or if you have a web camera. Okay, just try to answer it. Okay, if you have it, you just ready to have it. If you do not have it, just you just write it. You don't have it. And determine on this survey result, I will determine that what's the format for our first midterm. Okay. Be aware that our first midterm is coming very soon. Okay. We will coming. If things goes as planned, it will coming from we will have our first exam in the first week of the October. Okay, which will cover the first 3 chapter problem. Okay, so take time to also answer this survey. 3 things. Assignment due next week. Do not forget the second thing. Do not forget this attendance quiz for today. The last thing is that take time to answer this survey for the midterm. All right. Anyone? Any question? No. Okay.
No.
Yeah. Okay. So I will see you next Monday. Okay. Bye, everyone. Yeah.
Thank you,
Have a good
Professor.
weekend, Professor.
Yeah. You too.
Bye, Professor.
Bye.
Professor,
Yes.
if you just have a minute, I just want to ask a question about something earlier in chapter 2. So it was through like the different differentiation between streamline, pathline, streakline, all that stuff. I actually think I have some sort of understanding of that. What I don't really understand is a timeline and whether or not, like, is it relevant to what we're going to need to know? Like, come on.
For the timeline, it's very simple, to be honest. Okay.
Okay.
Timeline is, you think about timeline, it doesn't want to track the surface, try to propagation of surface. So basically, you can drag, you can draw any surface, you can choose arbitrary point length, right? And then you want to see that with time going, where this surface will go. That's it. That's the whole meaning of the timeline. I'm talking. So it's like a timeline, just like a, if this is you have fluid coming from this orifice, okay. And for example, in the beginning, I draw a line here. I try to arbitrarily select particles at t equal to 1. I draw a line here. I want to see that at t equal to 10, what is line will going to like? Maybe it's going to like something like this. So it doesn't want to track any arbitrary intersurface. Example can given is that like I don't know if anybody do smoking, okay? Like somebody when they smoke and then they can put if this is mouse, right? I don't know what the English word, so they can make this circle of smoke going out, right? So this smoke will this equal to t to 0. So I arbitrarily put this as a line here, and then at t equal to 1, then this become larger. So this is like a timeline to track that how this surface is become larger and larger as I'm talking with the time. So this is a timeline. You understand what I'm talking?
Professor, that might have been the best example I've ever heard.
Okay. All right. So yeah, that's it. So if you have more questions about this, you can go to my, I have my office hour on Wednesday, so you can just talk to me on the Zoom.
Here's just something I want to let you know. The problem with that is a lot of professors for the classes that I've been have conflicting office hours, and I actually have a class during your office hours, so it's nearly impossible for me to come unless I skip class. So that's why, like, I just, if I have any questions, I try to ask them in class or I ask them after class.
Yeah, I'm a little bit free on the Wednesday afternoon. Okay, so when your class will finish?
Let me double check. I'm sorry, I'm very I haven't memorized my schedule yet.
Okay. So,
I finish class at 4 o'clock.
Okay, so if you need it, you can write me an email so we can find a small time after 4 o'clock at Wednesday, so we can talk. You can just write me an email to make an appointment for that.
Okay. All right, fine. So then I'll do that. Just one more thing. I just want to clarify. So a pathline is basically a fluid particle's trajectory. A streak line is basically a line connecting all the path lines of different particles. And then the streamline is basically it's the tangent to the velocity vector.
Yeah.
Like a curve to, okay, fine. I just wanted to make
sure. You understand it's correct. Yeah.
Okay. And then, and for steady state, they're all the same. And when it's unsteady, that's when you're able to see differentiation between between them all.
Yes.
Okay. All right, great. Thank you so much, Professor. I'll send you an email regarding office hours.
Okay. All right. Take care.
Have a great weekend.
You too. Bye, everyone.